Okay, we're going to continue on here, chapter whatever, 12, kinetics. So last time we talked about specific orders of reactions, I believe. So we saw first order, we saw second order, and we saw zero order, which are common orders of reactions overall. Each of them has what's referred to sort of as an integrated rate law for each of these things. Like the natural log of A is equal to natural log of A naught minus KT, 1 over A, thank you, equals 1 over A naught plus a KT. And like concentration of A is equal to the concentration of A naught minus KT. We talked about specific sort of units for the rate constants as well, which is really important. So again, 1 over seconds or 1 over a unit of time is typically the units that we see for a first order. 1 over molar seconds, or really, again, a unit of time there is for second. And for zero, because it's zero order, we'll have really the same units as the rate, which is molarity over seconds. Once again, this is really important, as we talked about, because they will not always tell you sort of the order of the reaction. They will give you the rate constant with the units and expect you sort of to know what order it is, so that you could choose sort of the correct integrated rate law. We also saw some half-life equations with each of these. Second and zero, also the initial concentration is important for the half-life as well. We saw some graphs as well. Typical linear relationship that we see for a first order graph is natural log of A versus time there, and we get a straight line where the slope is equal to minus K. For second order, it does have actually a positive slope line. Actually, we'll go in this direction, and M would equal K. And lastly here, concentration versus time will yield us again a straight line where the slope is equal to minus K. In addition, at the end there, we started talking about energy and temperature relationships. And we saw some energy diagrams, right, where we have our activation energy. And that activation energy, again, is the hill that the reactants has to climb to get to the other side. Again, the difference between where the energy of the reactants and products are is our delta H for that reaction. And we saw the Arrhenius equation, which basically relates sort of temperature to the rate constant. And we saw really this version of it, I think, at the end there. This is the sort of graphical version of this equation. This is the one we typically use to make a Arrhenius plot. And this is in the form of a straight line. This is our y is equal to, this would be our mx plus b in this case. And that means that the typical graph that we see plotted here is the natural log of K on the y, and 1 over the temperature, which does need to be in Kelvin, by the way, when you do that. And it should yield you a, really, in most cases, a negatively sloping line here, where that slope will equal minus E of A over R. R is a gas constant, and remember that the R in this case is really this gas constant right here. It is the one that has the energy value in it. It is not the one that we use for like the ideal gas law or anything like that. So it's the 8.314 version of the gas constant there. So graphically, you can make a graph like this. You could take the slope, and as we talked about last time, since the line here is going to be really a negatively sloping line, along with this negative, we'll turn our activation energy into a positive number, which is what it should be. So you should typically get a positive value for your activation energy. I will say, in terms of units, we'll see another version of this equation shortly here. In terms of units, you do want to be careful. These two, activation energy is usually given in kilojoules, and the R there is usually given in joules, as we see there. So you will be off by a factor of 1,000 if you're sort of doing a calculation involving those two numbers. You do want to make sure that you keep an eye on that. By the way, the y-intercept here would equal the natural log of A, which would give you your frequency factor. which is sort of the proportion of molecules that have enough energy to kind of get up and over to the other side. So graphically as well, you could use your equation, actually solve for the frequency factor using this equation. So I say this equation is definitely used in most cases for sort of plotting and to make a plot. So let's take a look at one here. So let's say we had a problem like this where we want to determine the activation energy and the frequency factor for this reaction. We have a bunch of these values here. So we have our temperatures and we have our K values. So in this particular case, our temperatures are in Kelvin, so we don't have to convert it to Kelvin. But once again, if they were in Celsius, you would need to first convert them to Kelvin. And then what we really need to do, right, for all of our temperature values in this table is take 1 over the temperature, and that's what's going to be plotted on the X. For all of our K values that are in this sort of table, we need to take the natural log of each of those values, and that would be what would be plotted on the Y. And that would get us our plot here of our natural log of K versus 1 over the temperature. So if you do that, it will look something like this here. And if we get our equation there for our line, it will be the same as what we see on the screen here. Y is equal to minus 1.12 times 10 to the 4 x plus 26.8. Again, that is our Y is equal to mx plus b. So we could use this information to figure out the activation energy in this case. Again, the slope in this case would equal minus E of A over R. So we can basically find our E of A by taking minus R times our slope. And again, we got to make sure we do take the negative to the other side as well. When we do that, this is our slope, which should include the negative. That's what's going to turn it into a positive value. And we would take our E of A here is equal to minus 8.314 joules per Kelvin per mole. And we will take our minus 1.12 times 10 to the 4, it looks like, as well. So if we do that, we will end up with 8.314 times 1.12 to the 4th, an E of A of about 93,116.8 joules per mole. And if we did a little bit of kilojoules, which it typically is given in, maybe clean it up to 91.3 kilojoules per mole would be our activation energy in this particular case. Any questions on that? And by the way, the kelvins cancel out from the slope value, basically, right? Rise over run. So it'd be like basically it's Kelvin on top. Now for our activation energy, which is the not activation energy, for our frequency factor, that's the other thing we're looking for right there. For our frequency factor, that is equal to the y-intercept. So the y-intercept will equal B will equal the natural log of A, right? If we look at that equation. So in this case, our y-intercept is 26.8, would equal the natural log of A. In this case, to get rid of the natural log, we do need to take E on both sides there, right? So we'll do a little E action there, both sides. That's going to get rid of that, and that will give us an A of, in this particular case, if I hit the right button, it'll give us an A, maybe 26.8. About 4.36 times 10 to 11. Now, typically speaking, the units associated with the frequency factor will typically be the same units that you find for your rate constant. So those would typically be the same units, and we will end up with basically those same units for this particular guy. The reason for that is when we take the natural log of K, there's no units. But now when we take the E back of it, we would get the same units basically back. So we kind of get those units back that way. So typically, frequency factor will typically have the same units as the rate constant in terms of the units that you end up with. Any questions on how to graphically do this? Now, clearly in class, you would not be asked to graph this by hand. Maybe you would if I'm mad at you. No, I'm just kidding. You would not be able, but maybe you might be given the graph with the equation. So you need to be able to obviously use that information to calculate these type of things. Any questions on that there? And I think I mentioned it last time as well. Some of the homework problems, you may have to make some graphs to sort of answer as well. Yeah. All right, so let's take a look at another version of this equation. And there's really, in addition to this version of this equation here, there's a few other versions of this equation as well that you might see. You'll see a different version in the lab manual, I think, but it just kind of depends on sort of what they do with the He's on the right-hand side. This is what's sometimes referred to as the 2-point version of this equation. This is if you only have 2 points along that line, you could sort of mathematically solve it. And probably in most cases, this will be probably the version of the equation that you would use in most cases. This is the natural log of K2 over K1. So these are our rate constants at 2 different temperatures. This is our activation energy. That is still the same 8.314 version there. And these are our 2 temperatures, which obviously needs to be in Kelvin as well. This is definitely the one where those units I was talking about earlier come into play. People always sort of forget, again, kilojoules is typically what we see, again, for our activation energy, and ours in joules. You do need to do a conversion. So whichever way you want to do it, you can convert to kilojoules to joules or to joules to kilojoules. But if you're using those two together, you got to make sure that you do that conversions. So this is one of the versions of this equation. A couple other versions of this equation is they sort of distribute the negative out of the parentheses, and you do like 1 over T2 minus 1 over T1 with the negative on the outside. Another version of this equation is they combo the denominator there, do like T1 times T2. So there's like 3 different versions of this equation. So you might see some different ways that this equation is written. If you choose any of the correct versions, including this one, they all should come out the same. Like I said before, I think in the lab manual, they distribute the negative out of the parentheses and flip everything around in terms of the 1s and the 2s. So again, it's the same sort of equation, just things distributed out. So why don't we try it then? In the reaction, we have a rate constant at 2.5 at 701 and 567 at 895. What is the activation energy? Let's take a few moments and see what you come up with here. Okay, so let's take a look. So obviously we have 2 rate constants here. We got a K that is 2.57. And we have another temperature there, 701. We have another K at 567. And our temperature at 895 Kelvin. And we're looking for the activation energy here. In this case, our temperatures are in Kelvin, so we don't have to do anything with it. I'm just going to call the first ones 1s and the second ones 2. It really doesn't matter as long as you keep, obviously, the values that go together. We'll use our natural log here of K2 over K1 is equal to E of A over R, 1 over T1 minus 1 over T2, I believe. And I think we're good to put everything in. We'll go with the natural log of 567 divided by 2.57 equals our E of A, which is what we're looking for, 8.314. And again, here our 1 over our first temperature, which is 701 minus 1 over 845 Kelvin in this case. All right, so I'm just going to kind of clean up a couple of things. By the way, you do divide first and then take the natural log of it. Don't take the natural log of both of them, right? So maybe if I do a little bit of that, I'm going to get on the left-hand side, 5.39645 equals our E of A over 8.314. If I clean up what's inside the parentheses there, 1 over 701 minus 1 divided by 845, gonna get me a 0.000243. At this point, I need to multiply the 8.314, and then I need to divide what's in the parentheses, right? Yeah. What's that? It probably is. That would probably be good. Thank you. It's kind of like that, but no, it's it. I was just making sure you're paying attention. I didn't screw up that bad. I screwed up pretty good. Let me fix that up there a little bit. I guess that's why they invented erasers even on tablets. All right, so 0.00309215. Thank you. All right, so let's try this again here. We're going to take 5.39645 times 8.314. We're going to divide it by our correct number now there in the parentheses. And that is going to get us a E of A when we do all of that of 14503. And these are going to be joules here. Again, typically given in kilojoules, so I'm going to divide it by 1,000, and I'll call it about 145 kilojoules in this case. Yeah. Again, a positive number, so it should be a positive number when we get our activation energy. Any questions on that there? All right, so let's try another one here, maybe. So as we talked about earlier, oftentimes we talk about the rate doubling for every 10 degrees Celsius rise. Calculate the activation energy. In this case, there's a hint as to how to do it there. Okay, so they chose basically a 10-degree spread here in terms of our temperature, and they already converted it to Kelvin, which is good. We know that the rate's going to double, so really the end result of this should be a 2, basically, so that it will be doubled, and that's what this is relation to here. Basically, our K2 is twice as fast as our sort of K1. So that's going to essentially give us our natural log of 2 times K1 divided by K1, which once again will give us basically our 2 over there. Our E of A over our 8.314. We're going to go 1 over our T1, which is 300, minus 1 over our T2, which is our 310. Once again, here we'll take the natural log of 2 on the left there, and that's going to give us 0.693 is equal to E of A over 8.314. And if we clean up the parentheses there correctly this time, hopefully, there we go with 0.000175. Going to do the same math here. We're going to multiply and then come back through and divide to the other side what we got in the parentheses, and that will get us here. About an E of A 53364. Again, these are point dividing by 1,000 to convert them into kilojoules. About 53.4 will go. Any question on that calculation here? Yeah.
Celsius is just like a.
It's not. It's really how they chose these temperatures. Yeah. So this sort of shows sort of like a room temperature-ish type of one. I think the first one's like 80 degrees or something like that, or something in that ballpark, rather than 77. So they chose something that wasn't just a high starting temperature, kind of around room temperature. But you could really choose any sort of 10-degree difference in this problem. You'll get various amounts of activation energy difference, but it'll be in the same ballpark, unless you go super high in terms of temperature, starting temperature. Other questions? So this is the equation that we use really when we just kind of want to mathematically solve for, say, activation energy. But by the way, although we did a couple examples here of solving for activation energy, you could really solve for anything that's in that equation. So you could solve for K2, K1, T1, T2, and stuff like that. So really the only thing you can't solve for is R, which is a constant. So we you do have to be able to solve for anything that's in that equation. Any questions on that there? All right. All right. So as we talked about last time as well, when a reaction takes place, what happens is we do break all the bonds on the reactive side, and we do make all the new bonds on the product side. But in order for that to happen, you need two things, as we talked about, to sort of occur. You do need a collision to happen, and they do need to kind of hit each other in sort of the active spots on both sides for a reaction to take place. And they need to hit each other sort of in the right amount of energy, which is sort of like that activation energy that they need to get to the other side. So, for example, here, if we kind of collide with the purple part in this situation, it will lead to products being formed. But just because they run into each other in this direction here with more of the carbon side, it will not actually lead to products being formed. So sometimes people think all you need is for them to kind of come together, but they do need to come together in sort of the right location with the right amount of energy in order for products to be formed. So this brings us to an important idea of reactions as well, which are referred to as reaction mechanisms. And not all reactions, for example, happen in a one-step sort of situation. A number of reactions occur in multiple individual reactions to which you add them together. So, for example, if we had, you know, A plus B goes to C plus D, then maybe C plus D goes to E plus F. If we were to add these reactions together, when we do add reactions together, anything that's on opposite sides of the arrows that are the same could either cancel out or reduce down. It's like subtracting. You can think of the arrow like an equal sign. So the C on this side would cancel, the D on this side would cancel, and that would leave us our overall reaction of A plus B goes to E plus F. This is very similar to, as you might remember, everybody's favorite thing, which was Hess's law. Yes, perhaps. Where you took a bunch of reactions, delta H values, you put them together in some weird combinations to figure out the delta H of another reaction. So some reactions happen, sort of in a one-step process. A lot of them happen in multiple step processes as well. So when we talk about reaction mechanisms, that is sort of what we're looking at. We're looking at a process where we could try to describe how this reaction is basically taking place. And the overall reaction is basically a combination of what are sometimes referred to as elementary steps or elementary reactions. These are the individual reactions that get added together to give us the overall reaction that's happening. So, for example, if we look at this reaction here, we have 2NO goes plus O2 goes to 2NO2. But during this process, N2O2 is detected. Although we do not see N2O2 in the overall reaction, but it is detected as the reaction is taking place. That means that it has to be sort of made early on in the reaction and then sort of get used up by the time the reaction's over with. And one way that we could propose that maybe this reaction takes place is a couple of these NOs come together to make the N2O2, which is why it can be detected. Then that N2O2 and oxygen react to make our NO2. And these would be sort of the elementary steps in this reaction where if we were to add these two equations together, the N2O2 would cancel out, and that would leave us two NOs on the left plus an O2 on the left goes to 2NO2. So this is sort of a plausible mechanism by which this reaction could take place. It also explains why we see the N2O2 being made during the reaction and it's not there at the end. That is what we sometimes refer to as an intermediate, something that's sort of made earlier on and then sort of used up as the end of a reaction. So intermediates, like in this case of the N2O2, are substances that are made in a reaction mechanism early on, but they do get completely used up by the time the reaction is over, which means they are no longer there at the end of the reaction. So typically speaking, intermediates are not found in the overall reaction. They're sort of a byproduct of how the reaction is happening. Made early on, gets used up, not found at the end of the reaction. And that, again, in the example we just looked at, it would classify what N2O2 would be in this case, as it's clearly made early on and used up. So that's a really important distinction. It is possible to have some things reduced down during the process of a mechanism, but still be there at the end, which would mean that they are not intermediates if you still see them at the end of the reaction. Now, when we talk about the molecularity of a reaction, and when we talk about elementary steps, there are unimolecular reactions. Unimolecular means one. So it's basically a reaction where there's one thing reacting. Bimolecular means that there are two molecules reacting in each elementary step. Termolecular means there are three reacting. So each of these would be considered bimolecular, as they both have two guys reacting in these elementary steps. So what is the idea here behind sort of mechanisms? One of the main sort of things that we try to answer in a mechanism type problem is this a plausible mechanism, or just a possible way that this reaction can take place? So we oftentimes will try to figure out, is this kind of a good or bad mechanism for this particular reaction that we're looking for? And a couple of things that we could do to help us decide that is, when we look at these elementary steps, and this is the only place really in kinetics where you could do this, is sort of when you're doing mechanisms and looking at elementary steps, is if you remember earlier on in this chapter when we were talking about calculating the rate law, that the orders for everybody, right, was not the coefficients. And it was found experimentally, right? We had our table, we did our rate 2 over rate 1 calculation and all those type of things. This is the only place sort of reaction mechanisms that you can use the coefficients as the orders. And you could actually write a rate law for each of the elementary steps. So for example, here, we could write a rate law for this one based on our reactant, and it would be the rate is equal to K times A, and it would be to the first, and we could use the coefficient here. Here, this would be the rate is equal to K times A times B. This is essentially 2A, which is where the 2 comes from in this case. So the one and only place that you can use the coefficients as the exponents are the orders is when you're doing mechanism problems and you're doing elementary steps. You could actually write rate laws for each of the elementary steps. So what are we going to do with these elementary steps and these rate laws? As I mentioned before, there's really a main type of mechanism type question, which is pretty much, is this a good or bad mechanism? Is this basically how this mechanism can occur? In order for a mechanism to be sort of a good mechanism, there's a couple of things that has to happen. The first thing is, when you add up all the steps for the mechanism, it needs to equal the overall reaction that you're looking for. So that you'll have like an overall reaction that you're trying to figure out, is this a good mechanism for? When you add up all the elementary steps, it obviously needs to equal that equation or reaction. If it doesn't, then obviously it's not a good mechanism. If you do add up all the steps and it does equal the reaction that you're looking for, then it's a good mechanism so far. The second thing that has to happen is what is referred to as the rate determining step. The rate determining step is also sometimes referred to as the RDS, for rate determining step. And that is the slowest one, or slowest step in the mechanism. And when you solve for the rate determining step based on the mechanism, it does need to equal the rate law that is found experimentally. So oftentimes in these problems, they will give you the rate law and go, hey, the rate law was found experimentally to be this. And when you look at the mechanism and you determine what the rate law should be based on the mechanism, the rate law from the mechanism and the rate law that was found experimentally, they should match each other identically in order for it to be a good mechanism. If you do that, and we're going to do some examples shortly of that, and they do not match, then it is not a good mechanism. It's not a plausible mechanism. What is the rate determining step? As I mentioned before, it's basically the one that determines the overall rate of that reaction. It's kind of like the guy in the 10 items or less line with 400 items, right? So before you could get through that line. You have to wait for that slow person ahead of you to kind of get through it. So that's basically what the rate determining step is. I'm assuming why there's a turtle there as well, as it's the slow step in the mechanism. All right, so let's talk a little bit about some of the ways that we go through this. And so why don't you try this one here and see what you come up with. What is the equation for the overall reaction? What is the intermediate? And what can you say about the rates of step 1 and step 2 in this mechanism? So take a moment, try to work through that, and we'll talk about it here. Okay, so let's take a look. So first one, we want the overall reaction. So we have the two-step mechanism here. So to do that, we're just going to add these together. Again, we're going to cancel out or reduce down anything that can be done on opposite sides of the arrow. To me, it looks like a little NO3 could go away. We also could maybe get rid of an NO2 as well. Again, everybody on the left-hand side of the arrow stays there. That means we'll have something like NO2 plus CO. Everybody on the right-hand side stays there. A little NO and CO2 in this case. Any questions on that there? The intermediate in this case is NO3. Anything else? NO2. Is NO2 an intermediate? It actually is not. And why is NO2 not an intermediate? It's still there, right, in the overall reaction. So although it did reduce down in this case, it is still present in the overall reaction, which means it can't be an intermediate. Definition again of an intermediate is it has to appear early on in the mechanism and then get completely used up by the time the reaction's over. So not appear in the overall reaction. So in this case, it is just the NO3 that would be considered an intermediate. Now we want to talk about the rates of each of these steps. So these are elementary steps, which means that for each of these steps in this mechanism, we can write a rate law for each of these. So if we were to write the rate law for step number 1, we would end up with a rate that is equal to K times NO2, and we would square it because that's basically 2 NO2 in this case. It's basically this, right? And here again, we can use the coefficient in these rate laws for these elementary steps. That is okay. That is the only place you can do it. Now for step number 2, the rate would equal K times the concentration of NO3 times the concentration of CO, right? And these are the 2 rate laws that we could write for each of these steps. We could use this to help us determine sort of which one is maybe faster or slower. Now, the rate determining step, which is the slow step, right? That is the slow step we just talked about. Which step in this mechanism would be the rate determining step? Yeah. For the second one? So rate laws are only about reactants. So we're writing specifically for this second reaction. So it'd just be those 2 there. Yeah. Yeah. So we're not really writing the rate law for this guy yet, but we're writing it basically for these individual steps here. Other questions? So the rate determining step, right, as we talked about a second ago, should match what? Should match the experimentally found rate law, which was given to us in the problem, right? The experimentally found rate law is this guy, right? And which step matches that? Step number 1, right? So because step number 1 has the exact same rate law as the one that was found experimentally, that means that step number 1 in this case is our rate determining step, which means it is our slow step, right? Which means in terms of relative rates, step 1 should be slower, right, than step 2. Step 2 should occur a lot faster than step 1 in this case, or however you want to word it in that case. Any questions on that there? So this is what I would classify as a one type of mechanism type problem where you're trying to figure out what the rate law would be overall. that is also going to be the rate law for the overall reaction because it will equal the slow step in the mechanism. Any questions on that one there? All right, so let's take a look at, why not? Let's take a look at this one. There we go. All right, so we have a 3-step mechanism here. And we're looking to figure out, is this a possibly good mechanism for this reaction? This is our experimentally determined rate law in this particular case. All right, so remember that 2 things. We need to make sure that all the steps add up to the overall reaction in order for this to be a good mechanism. And secondly, the rate determining step needs to have the same rate law as the one that's found experimentally. So those are 2 types of things that we want to sort of determine in this case. This type of mechanism problem, I sometimes think of it like a proof, like you know the answer, but you got to kind of prove that it matches, sort of deal. And that's sort of what's going to happen here. So let's start with the first thing. In order for this to be a good mechanism, when we add up all these steps here, we do need to end up with that reaction. So if we look here, that and that will cancel. I think with this guy here and this guy here will cancel. And I think that is all the canceling that we got going on. So everybody on the left-hand side will stay there. So we got 2NO plus we have 1 and 2 H2. Right-hand side, we have 1 and 2 waters. And we have an N2. So that is a check on that, right? So all these steps add up to basically the overall reaction. So that's looking good so far in terms of whether or not this is a good mechanism or bad. The next thing that we need to determine is which one is the rate determining step. In this type of mechanism problem, it's really hard to determine sometimes what is the rate determining step. Which one would be the rate determining step in this one? Yeah, it would be the one marked slow. That would be the one that it would be. Yeah. So sometimes they will put these in these mechanisms next to each of these steps to say like fast, slow, fast. The one that is marked slow is our rate determining step. So this guy right here is our rate determining step. And what that means is when we write a rate law for step number 2, it needs to match the one that was found experimentally. And again, in order for this one to be a good mechanism. So I'm just going to clean up some of my scratch out here so we can kind of see everything again, I think. Okay. So if we write the rate law here for step number 2, and once again, we could use coefficients as the exponent. So the rate here would equal K H2 and N2O2. I guess before I erased it, what were our intermediates in this case? Our intermediates were N2O2, and I think we had N2O as well, right? So we had N2O in this case. All right. So these were our intermediates that we had in this particular reaction. This is our rate law that we get for our slow step. We want to compare these 2 and see if they match. Do they match? The answer is you don't really know yet, because what we have in this rate law for the slow step is actually a intermediate. So in order to compare whether or not they actually do match, you got to compare the old saying apples to apples. Yeah, so you got to compare things that do not have intermediates in it. And that way you'll really know. So at this point, we really don't know. Perhaps it does, perhaps it doesn't. So the way that we can solve for it is we actually need to get rid of, in this rate law, we need to sort of substitute out our intermediate for something that's in the overall reaction. In order to do that, we will actually use some of the other steps in the mechanism to help us do that. Now, when we look at the mechanism, the only other step that has N2O2 is that first step. And that first step is actually a reversible reaction, which is why the arrows are heading in both directions. There's a forward direction that's heading in this direction, and there's a reverse direction that is heading in the opposite direction. Eventually, this will reach chemical equilibrium, which means that the rate at which they're going back and forth will actually equal each other. So we could actually write two rate laws for the first step because it is a reversible reaction. We could write a rate law going in the forward direction. So I'll just put an F there, going from reactants to products, which would be K times NO squared. We could also write a rate law going in the reverse direction, which means in the reverse direction, this guy right here is our product, right? Is our reactant and not our product. And we could write the rate for our reverse reaction would be K times N2O2. So these are the two rate laws that we could write for this reversible reaction, one heading in the forward direction from reactants to products, one heading from products to reactants. And we have each of those things here to help us. And the way it's going to help us is, in this particular case, this rate here and this rate here, although we do not know what it is, will actually be the same number. Because that's what it means when it reaches equilibrium. They're going back and forth basically at the exact same rate. So although we do not know what that number is, we do know this is the same number. And what that allows us to do, because it's going to be the same number, is actually set both of these guys equal to each other. So we could actually set those guys equal to each other. And that would get us that K times NO squared is equal to K times N2O2. Any questions on that there? The thing that we're looking to solve for is actually the N2O2, which means we need to divide this K to the other side. And these guys would cancel. And that would get us K times NO squared over K is equal to our concentration of N2O2. Any questions on that so far? That is what we want to substitute out here, right? So now that we know what N2O2 equals, yeah. They are, technically speaking, that is K and -1, and is that equilibrium? Yeah. Although they are rate constants, which means they're the same number. Yeah. So they'll be the same. Yeah. But they are technically labeled sometimes different numbers as well. Sometimes they'll label them like 1, 2, 3, 4 for all the other ones as well. Yep. So now that we have what N2O2 equals, all that is going to go into our original rate law that we wrote for our second step. And that will now give us a rate law of the rate is equal to K H2, and I'm just going to put it in like I wrote it here, K NO squared over K. As we just talked about a second ago, all those Ks are essentially the same constant, right? Which means they will cancel out. And now if we reduce that down, we will end up with K times H2 times NO squared. And now we have a rate law that we could use to compare to the experimental rate law that does not have that intermediate in it and now doesn't match. Are they the same or different? These two are the same, yeah? So the one that we found for the mechanism, once we got rid of the intermediate, has the same rate law as the one that was found experimentally, which means, technically speaking, this is a good mechanism, or what they like to call a plausible mechanism for this reaction to take place. It doesn't mean it will always happen this way. It doesn't. It just means this is a possible way that this reaction can take place through this sort of mechanism. Any questions on it? Yeah.
Did end up having with the slow step, if they already matched from the beginning, we don't have to do this, or do we still have to?
You wouldn't have to do this in this case. If it did match, then it would be basically a good mechanism. I would say a lot of this type of mechanism problem, which is a little bit different than the first one we did, in this type of mechanism problem, it's kind of like you need to prove that that mechanism is good or bad. And that's usually meaning you also do some substituting in to solve for it. Other questions? All right, I did one. Why don't you try one? See how it goes. Yeah. Let's say that. That's not it. Let's try that one. All right. Show that this proposed mechanism for this reaction, that 2 is way up there for some reason, which will get put it where it should go. matches the rate law that was observed. So give it a go, see what you come up with. Prove it's good or bad. And so once again, we want to kind of prove if this is a good or bad mechanism. And again, the two things that we need to make sure of is, does the elementary steps add up to the reaction we're looking for or equation we're looking for? And does that rate determining step have the same rate law as the one found experimentally? So this is our experimentally found rate law. This is our overall reaction. So we'll start with that. We'll add it together here. Looks like O is going to go away. And I think that's it, if I'm not mistaken. So we'll have 203 goes to 302. So that part of it is good. It checks out. Once again, if they do not add up to the overall, then it's a bad mechanism and it's not a good one. In this case, we know that the one listed as slow should be our rate determining step for this mechanism. And that's really the rate law that we want to match the one experimentally here. We also know that our intermediate in this case is oxygen here, our O. So the rate law for our slow step here would be K times O3 times O. Once again, we cannot at this point really sort of compare because we do have that intermediate here in this rate law. So we do need to kind of get rid of it. In this case, really the only option to get rid of it is going to come out of this reversible reaction here in the first step. And again, for that first step, we could write two rate laws going in the forward direction. It would be K times O3. Going in the reverse direction, it would be K times O2 and O. Once again, this number here and this number here should really be the same. That means, again, we could kind of set them equal to each other, and that will give us K times O3 is equal to K, O2, and O. In this case, we are trying to get rid of our substitute out for the O, so we're going to take these guys and divide it to the other side. And that will get us basically here K O3 divided by K O2. O2. And that will equal our O. That is what we're going to take into here and substitute that into there. And that will get us a rate law of K, and that is O3 times KO3 divided by KO2. Doing a little bit of cleanup here. We obviously have these Ks that will sort of cancel. We also have two of the O3s. So that'll essentially give us a rate that's equal to KO3 squared divided by O2's concentration, right? So now we have a rate law. I'll write it over here. It's got a little crowded there. O3 squared. O2. There we go. Now we have a rate law that we could compare. Do they match? They do match. Remember, this is to the -1, which means 1 over it, right? And that's basically what we have here, right? 1 over O2. So they do match in this case. And that means, again, this is a plausible, good mechanism for this reaction to take place. Question on that type of problem there. Again, I would say this is sort of a different type of mechanism problem where you sort of have to kind of prove whether or not the mechanism is good or not. Yeah.
Yep, the like overall equation, and the mechanism like checks off with the other one. At that point, once we do all this work, like the calculation is just to prove that it does.
Yeah, it's kind of like a math proof, right? You got to prove this, right? So yeah. So the work is actually the proving part of it, that it matches or not. Yeah. And again, although these two did match and they were good mechanisms, again, they may not be a good mechanism. So that is a possibility.
Saying that just tells you on that.
Yeah, so that's sort of what it's asking here is sort of, prove that it matches or really prove that this is a plausible mechanism. Some of the questions will just straight out ask you that, and it might even give you several different mechanisms and go, you know, which ones are plausibly good mechanisms or not. You may have to do it for different numbers of mechanisms and some. Uh, I'm good with good or bad. It's good. Yeah, it's good or bad. I get the idea. Is it good or bad? But they oftentimes will use the word plausible or as not plausible type mechanism in books and stuff like that. But it basically means it's good or bad. Basically, is sort of what that means. Other questions?
Assume that K is equivalent to inverse, so we just allowed to drop it on the.
Was that?
When we're like writing a fraction, we have to write the K out front both times if they just cancel out.
I'd like to see the work of it if you don't mind. Yeah. Other questions? All right. So this is another type of mechanism type problem. So why don't we try this one? Determine the overall reaction. What is the rate determining step? All right, since we're getting to the end, let's take a look at this one. So in this case, we want the overall reaction. So why don't we start with that? And that just is going to be bound by adding these together. In this case, it looks like B will cancel, and I think that's it. We have two A's on the left and a B2. On the right-hand side, we have two ABs. So this should be our overall reaction. We know the rate determining step is which step? It is step one. That means that although nothing was given to us in terms of the rate law for this mechanism should be the same as the one we have for step number one in this case, right? So if we write the rate law here for step number one, it would be K times A times B2, and that would be our rate law in this particular case. And I think we already did the intermediate, which would be B in this case, yeah. So in this type of problem, we're not really trying to prove anything. We're just going to try to figure out what the rate law would be based on this mechanism. And since that first one is a slow step, it should have the same rate law as the one that would be found experimentally. Question on that one there.